Good afternoon, everyone, and welcome to today's webinar on the essentials of stainless steel, case studies in corrosion, hosted by Chemical Investigation Services and Creamer Media's Contract Publishing. Thank you for taking the time to join us. And we're looking so forward to hosting you. I'm Shannon Derejo from Creamer Media's Contract Publishing, and I'll be your host this afternoon. Today's webinar aims to expose engineers and designers and process engineers to the basics of stainless steel corrosion by means of interesting case studies. We'll also highlight the expert services of Chemical Investigation Services in stainless steel corrosion and failure investigation. Please note that we'll answer all your questions at the end of the presentations, so please be sure to send your questions via the live Q&A, which you'll find on the panel at the bottom of your screen. And don't worry if you miss anything during the presentations, as we are recording the webinar and we'll be sending the recording to you when it's available. Chemical Investigation Services has been serving South African industry since 2004, and specifically in corrosion and failure investigation since 2008. Our main presenter today is Simon Norton, who has over 30 years of corrosion and failure investigation, chemical and petroleum product experience. He graduated from the University of Cape Town with a Bachelor of Science degree in chemistry and is a member of the South African Chemical Institute, the Corrosion Institute of Southern Africa, as well as the UK Institute of Materials, Minerals and Mining. Since 2008, he has consulted to industry focusing on independent investigations, corrosion assessments, corrosion testing and material selection, with a special emphasis on stainless steel. He has also carried out various failure investigations where materials, corrosion, and analytical chemistry knowledge were required. I'll now hand over to Simon Norton from Chemical Investigation Services. Over to you, Simon.
Good afternoon, everybody, and thank you, Shannon. Thank you so much for your introduction, and good afternoon to everybody listening from around the world. I'm going to start out in this webinar with really just a touch of what is stainless, how corrosion is involved with stainless steel. This is not a comprehensive course. This is an introduction. It will give you a feel for the many concepts that we are going to speak about. I will be using some visuals now to lead you through the start and look at stainless steels. The ins and outs of stainless steels. Firstly, the family of stainless steels are essentially split up into 5 families. The austenitic stainless steels, whose structure is face-centered cubic. And for those of you who are not metallurgists or chemists, don't worry. These are just some of the concepts that we're going to introduce you to. Ferritic stainless steels, which are magnetic. And by the way, austenitic stainless steels, which you're familiar with as 304, 316, and there are others, are non-magnetic, or so they have a special property which you can often check for. DUPLEX stainless steels, which few engineers that I've come across seem to know about, but which are very, very useful. Martensitic stainless steels and precipitation hardened. I'm going to be largely dealing with austenitic and DUPLEX stainless steels in this short webinar today. Just to give you some idea of the common stainless steels which you might come across and their compositions, 304 stainless steel, obviously containing iron, a small percentage of carbon, and then 18% chromium, 8% nickel. 316 stainless steel contains a percentage of carbon, 17% typically, and this is typical values, chromium, 10% nickel, and 2% molybdenum. Now, we're talking here about 316. If we were talking about 316L, we would be meaning the low carbon 316. And many people that I've come across find that they implement 316, but forget that they must order the 316L, which is low in carbon and therefore a value when you're welding stainless steel. Then the DUPLEX stainless steel, one particular one is DUPLEX 2205. Now, this is a completely different type of material, but we'll talk about that in a minute. And finally, the super austenitic 904L. Now, somebody who registered for this course wrote us a question concerning the problem that he was having with his plant. We'll deal with that and address 904L later in the webinar. While there are many other forms of corrosion that affect other materials, the main areas that we're going to look at are pitting corrosion, crevice corrosion, which we know as localized corrosion, stress corrosion cracking, and intergranular corrosion. They are the main corrosion types that are associated with stainless steel. I'm not going to spend too much time on each of them, but I'm going to give you a feel for them so that you'll at least be aware of the dangers that arise with stainless steel. Stainless steel is a strange material, unlike normal mild or carbon steel, which rust uniformly. And then, of course, when they severely rusted, they spall and come to pieces. Stainless steel, particularly stainless steel piping, can be very, very deceptive. You will see no uniform corrosion. Suddenly a pit will develop, and when that happens, you can have catastrophic failure. At a glance, the three stainless steels that I'm going to be talking about with respect to corrosion are austenitic, ferritic, and DUPLEX. Austenitic are non-magnetic. They're face-centered cubic. They cannot be hardened by heat treatment. You can harden them by cold working. They're very formable and weldable. They corrosion resistance, it's reasonably good, but you've got to be very careful when you weld them, so you must make sure that you choose the low carbon version. And you're familiar with them. Most engineers are familiar with 304 and 316 stainless steel. Ferritic stainless steel is ferromagnetic. The structure of the stainless steel is body-centered cubic. You can't harden it by heat treatment. It's got good formability. You can draw it. Its corrosion resistance is not as good as austenitics. And it's got stress corrosion cracking resistance, which is an advantage. And then, of course, there are the DUPLEX stainless steels. And I would like to emphasize to those listening, start to look at the DUPLEX stainless steels. They are enormously useful materials. For the same thickness of austenitic 304, 316, you could use a DUPLEX stainless steel at a much lower thickness and achieve far better performance out of DUPLEX stainless steel. So in our journey into stainless steel, we're going to get to know some stainless steels. We're going to find out where to use them, how corrosion resistant are they, and what can't they do and what can they do. Stainless steels can be used in decorative applications. So in this particular photograph that you're seeing, not only are they visually beautiful, but they are able to withstand the fact that they're passing over a river, which might well be semi-brine or semi-saline, and they will be faced with atmospheric and sea spray corrosion, and yet they are able to resist it. They are beautiful materials, but be very careful when you use them with respect to corrosion. Earlier on, I referred to the structure of ferritic stainless steels, and I said they were body-centered cubic. If you look at the cube on the left of the image, you will see that there's an atom at each corner of the cube and one at the center. If you then add nickel to that mixture, so on the left-hand side, you have chromium. If you now add nickel to it, you get an austenitic structure. And if you look at that, you'll see that it's face-centered cubic. In other words, there's one atom at each corner of the cube, and there's an atom on each in the middle of each face of the cube. Hence, face-centered cubic. And these structural differences in the very heart of these stainless steels make for the different properties. And they're vital to the performance of these products with respect to their mechanical strength as well as their corrosion resistance. If you look at the microstructure of the ferritic stainless steel on the left, as you add nickel, so you're going from an iron chromium mixture, an alloy of iron and chromium, and as you add nickel, you've got a DUPLEX material in the center, and then on the right-hand side, you've got the austenitic material. So we're going to be discussing largely the DUPLEX and austenitic stainless steels. Now, stainless steels are a family of passive alloys, largely of iron, with a minimum of 10.5 to 11% chromium that forms the passive chromium layer, the chrome oxide layer on top of stainless steel. This is the heart of the secret of stainless steel. The key other elements that are added in are obviously nickel, molybdenum, tungsten, nitrogen, and there are others such as copper, niobium, and those make for special stainless steel alloys. But essentially, once you've got your iron, chromium, carbon, nickel, molybdenum mixture, your alloy, you've got a passive alloy with very high corrosion resistance, a reasonable price, a beautiful appearance, as you saw in the photograph, and a high degree of workability. Now, as I take you through this journey on stainless steel, I'm going to start introducing you to concepts which you might not have heard of. And one of them is called the PREN, or Pitting Resistance Equivalent Number. Now, if you look at the equation at the top of the screen, you'll see that it's calculated by taking the percentage chromium in your stainless steel, 3,3%, or for those of you that don't use the comma, 3.3% times the percentage of molybdenum, and 16 times the percentage of nitrogen in your stainless steel. That number will give you a comparative tool for starting to look at selecting stainless steel. And just out of a matter of interest, chromium is known as a ferrite stabilizer, nickel as an austenite stabilizer. Molybdenum increases the pitting resistance, hence 316 stainless steel has molybdenum, and it has a better pitting and crevice corrosion resistance than 304, which has no molybdenum at all. And nitrogen has also been found to increase pitting resistance in stainless steel. So going back to the 5 forms of stainless steel, of corrosion that will affect stainless steel. You can have general or uniform corrosion. Yes, that does occur, but you will see that and you can actually measure it. So you could actually put in stainless steel coupons into whichever process fluid or application you're going to use, and you can measure weight loss over a period of time, and you can determine the rate at which your stainless steel corrodes uniformly or by general corrosion. But more insidious and dangerous are things such as stress corrosion cracking, crevice corrosion, pitting corrosion, and intergranular corrosion. And I'll touch on those briefly during the case study. So if you look at the visual that I've put up here, general corrosion, you can see on the top block, that rectangle is fully formed, nothing's happened. Then you can see how it's uniformly worn down. So if you can weigh the first block marked A, and then you can actually weigh the next one B, and then the final one C, you can get a weight loss and you can calculate a rate of corrosion per annum. So for those who work in the metric system, we would measure in millimeters or milligrams per annum, or some people measure if they're in the USA in mils per annum. But pitting corrosion, that's very dangerous. There you might get a break in the passive layer on stainless steel, a pit forms. It looks very small at first, but little do you realize that the volume of the pit is enormous under the surface, and that can lead to catastrophic failure of your pipe or structure or whatever else you fabricated. Now, this material that I'm showing you here, this data, essentially comes from a test that was carried out in the Middle East. And the idea was to test various forms of welded and exposed stainless steel to atmospheric corrosion and to also compare different surface finishes. Don't worry about all the detail that's on here, but essentially if you look on the left, you'll see the 3 families, ferritic, austenitic, and DUPLEX. Then you will see the EN number for stainless steel. Some engineers might not be familiar with it. Those of you that are, you will know where to look it up. Then the surface finish. Now, it is not important to know the various surface finishes that I've shown here. What is important to remember is that surface finish can seriously impact the corrosion resistance of your stainless steel. So how you surface finish your stainless steel and prepare it can have a huge effect on its performance in action in your plant. If you look on the typical chemical composition and you look under the CR and Ni, the nickel and chromium, you'll see that, for instance, the chromium content in the ferritics goes up. When you go to austenitics, 14301, that is 304 stainless steel. It's got 8% nickel, 18% chromium. If you look at 1.4404, then of course you've got slightly less chromium, but more nickel, and you've got molybdenum. This was used for an experiment, which I'm just going to show you some results of, to emphasize the importance of surface finish. These coupons were exposed in the atmosphere for 2 and then 4 years, and then they were as welded and prepared surfaces were then evaluated. So the base material is shown in the light blue and the welded area in the dark blue. And you can see that the maximum depth in microns in 2 years and 4 years has obviously slightly increased, but when they did a shot blasting and lab pickling, there was no corrosion. So impacting the surface has a huge effect. So in your design, you need to decide how you're going to treat the surface of your stainless steel. Now, I referred earlier on to the PREN number, and if you look on that chart on the right-hand side, you'll see the PREN numbers for various stainless steels, and you'll actually see that they increase, and some of them go right up to 56, and then for the duplex stainless steels, they're substantially higher than the austenitics, like 304, 1.4301 has a PREN number of 18, 316 has a PREN number of 24. But if you go and look at the duplex stainless steel, they've got PREN numbers of 35 and 43, the pitting resistance equivalent number. Now, how do we determine these these values? Well, that was determined through an equation, and there are different forms of it. But there's another way to determine this, and this is known as the critical pitting temperature. There is an ASTM method called D150, and I've just showed you here a typical electrochemical test cell. This one is not jacketed to increase the temperature, but I hope my cursor will show on the screen. If you look as my cursor moves around, the yellow probe that I'm looking at there, that is the reference cell in which against you measure. The two dark rods are what are known as the counter electrode, and the working electrode is at the bottom underneath here and connected through to our equipment on the right-hand side. And in the critical pitting temperature test, they set the voltage, which you would measure and set in your instrument, to 700 millivolts with respect to a standard calomel electrode. That's this electrode marked A in the photograph. Now, obviously, we haven't this is not jacketed to control temperature, but when we increase the temperature, every time we do that by 1 degree C, we evaluate what the current measure is. And when the current reaches greater than 100 microamps per square centimeters for a particular time, that is then the critical pitting temperature according to this method. This is a very useful value to use in design. And if you look at this chart that I'm showing you here, you will see that on the left-hand side is critical pitting temperature, and on the right-hand side, on the bottom axis, is the chloride content. And from these sorts of charts, you can work out where to use your stainless steel. Here again, you can see that different surface finishes have resulted in different critical pitting temperatures for duplex 2205 stainless steel. And again here, you can vary the response of your material by examining the critical pitting temperature. In this particular case, we're looking in the center, we have 316 stainless steel in aerated tap water. And for instance, if we have 1% chloride in the solution, then we're going to have a critical pitting temperature of just over 40 degrees centigrade. But if we only have 0.1%, we're going to have a critical pitting temperature much higher at that particular open circuit potential. So while you do not have to understand the detail of what I'm showing you here, the point I'm trying to make is critical pitting temperature is a very useful design parameter. This particular graph shows merely that if you've got a surface roughness of 0.2 microns and a surface roughness of 3, if you see where my cursor is at the bottom of the screen, if you look at the depth of corrosion that's occurred, you can actually see that if your surface roughness is very fine, you get less corrosion than if your surface roughness is rough, or a higher value. Let's put it like that, a higher value. So you've got many orders of magnitude from an RA of 0.2 microns to an RA of 3 microns. And you can see after 4 years, there's a difference between the two corrosion rates, the maximum depth in which corrosion has occurred. On the left-hand side, and this is for duplex stainless steel 2205, you can see the impact. The left-hand two pieces show a 0.2 micron surface. The one on the right, the two on the right are 3 micron surfaces. Now to some short-term practical discussion. I referred to pitting temperatures, but there's also crevices. This particular machine, going to see, has very sophisticated equipment on it. And if you look at the top here on the periscope, not only are there optical periscopes, there are electronic periscopes as well. And this is what they could look like. When this was designed, the top part here is made of a composite material, but the rest is made of 316 stainless steel. However, did anybody think about design? Because this device actually subsequently suffered from crevice corrosion because of the numerous crevices that the actual machinery required and couldn't be avoided. So how did we test for that? Well, we took the material, coated it in a test coupon, which you could see here in its rack, and we put a crevice former on it. And when we'd subjected it to an atmospheric test, or sorry, to a chamber test to simulate what would happen to it in the atmosphere, that's what it looked like under the crevice former. And if you look on the side where the arrow is, you'll see here that crevice corrosion has started to occur. So we can actually test for crevice corrosion via chamber tests in a laboratory. And in this particular case, this stainless steel has actually got a coating on it, and we had to see how resilient that coating was. And as you see here, there's close up, there are many crevices here, and we had to work to design a coating which would eliminate that problem without changing the material. A second case study in stainless steel selection in use is this particular machine, which is used to actually cook and flavor sausages. Originally, the designers wanted to use a mixture of 304 austenitic and 316 austenitic stainless steel. However, they couldn't succeed when they made their trial models. And through a set of test methods, a test that we did, we eventually advised them to use DUPLEX 2205 stainless steel. And here is the machine in operation. We initially set up and did a series of chamber tests using different materials in a rack. As you'll see here, we tested a variety of stainless steels, subjected them to an atmosphere similar to that found in the sausage making machine, and then evaluated them. In that particular case, all the plates were uncoated. In this particular case, we used different surface finishes. Some you can see have a mirror finish, some had been coated, and this test rack is after the test has been carried out. If you look along the bottom, you'll see we used DUPLEX 2205, we used super austenitic 6% molybdenum 254, we used austenitic 316, and we used another super DUPLEX SAF 2507. And then we've got different coatings and mirror finishes, and we wanted whether we could get away with a high mirror finish, but a much lower cost stainless steel. In the end, we went for the DUPLEX 2205, and in practice, it was highly successful. So going back and summarizing, if you look on the left-hand side, there are different stainless steel types, 304, 316L, 904, which we call a super austenitic, 2205, which is a DUPLEX stainless steel, 2507, also a DUPLEX. And if you look at the chromium content, that's the key to stainless steel, you'll see that it increases substantially. If you look at the nickel content, you'll see that the DUPLEX stainless steels are very low on nickel, and nickel's a very expensive material. So DUPLEX stainless steels allow you to get amazing performance out of your stainless steel, but without the cost associated with the nickel. The molybdenum is also there, and that's there to serve the purpose of fixing pitting corrosion and preventing it. And then you can look at the PRE numbers, the pitting resistance equivalent number, and then the critical pitting temperature, which you can see for conventional 304 stainless steel is less than 10 degrees centigrade. But for DUPLEX 2205, it's 52. This is just an example of how 304 stainless steel can severely pit and damage a plant. You can see close up what actually happens. This is the machine that was finally made with DUPLEX stainless steel. And in this particular case, this weld was a 304 weld at the same plant, 304 pipe, which should never have been there. The weld was not properly done, so of course the customer had a catastrophic failure and it had to be sorted out. And if you see that Arnold's going to talk about this in a minute, But if you allow your stainless steel to become covered with oxide, you're going to sacrifice your stainless steel, because where the heat tint occurs, you get depletion of the chromium in the stainless steel and the destruction of the stainless steel. This particular pipe also suffered from stress corrosion cracking, which I'll talk about a bit later. That just gives you an illustration of what it looks like. Well, I'm going to hand over to Arnold now and come back to you later. Thank you very much.
Thanks very much, Simon. I just want to say thank you for starting us out on that road to understanding the pros and cons of stainless steels when it comes to corrosion and choosing the right material for your application. I'd like to now introduce our guest speaker, Mr. Arnold Meyer, who is the Applications Development Manager in the Integrated Customer Solutions Department of AFROC South Africa. He holds master's degrees in metallurgical engineering and engineering management from the University of Pretoria. He's a certified international welding engineer with a comprehensive background in fabrication and heavy engineering and manufacturing. Arnold has experience in developing welding procedure specifications and welding application solutions for the heavy engineering, renewable energy, power generation, petrochemicals, and the sugar industry. He joins us now to provide a short overview as well as discuss the key issues when it comes to welding stainless steel. Over to you, Arnold.
Thank you very much, Shannon. Thank you, Simon. I'm just going to share my screen. All right. I will look at a short opening statement, and then I will look at the austenitics 304L and 316L, and the welding of the DUPLEX stainless steel 2205. As Simon said, DUPLEXes are very useful materials, but they are complicated to weld. So we will look a little bit at that. Starting out, before I look at all the key issues, I must state that most stainless steels, if not all of them, are easily weldable. If you understand the key issues, if you follow the correct procedures, and if you obtain advice if your organization does not have experience in the welding of stainless steels, and that advice is available. Now, if we look at 304L, that is probably the stainless steel that is used the most all over the world. It is a versatile material. It's got its limitations, but it's a very good material. The key issue there, the number one, and that's true for all austenitics, is the first issue, and the most important one, is solidification cracking of the weld metal upon solidification. The second issue is pitting due to carbon contamination from carbon steel. And the third one is the discoloration and scaling due to high temperature oxidation. And that's the discoloration that Simon referred to. The solution for the solidification cracking of 304 is to weld it with a 308L type electrode. The 308L type electrode places it into a region where upon cooling you will form a small percentage of ferrite first. That's called primary ferrite or delta ferrite, and this then go and sit on the austenite grain boundaries, and it prevents the low melting phases to migrate to the grain boundaries, and by that mechanism prevent the hot cracking. The pitting due to carbon contamination, very important in any stainless steel welding, is to physically separate carbon steel and stainless steel welding operations from each other, and use dedicated stainless steel brushes and carbide-free abrasives. Whenever your stainless steel is hit by grinding sparks from carbon steel, a pit will form there. Because of sensitization, the carbon reacts with the chromium, they form chromium carbides, and because of that, there locally on that spot, the chromium will be depleted in the stainless steel and pitting will occur. The discoloration and scaling, HP argon as backing gas for open roots, especially in pipes, because after you welded the pipe, you can't go and clean up there. So you need to purge with an inert gas to stop the oxidation and discoloration. And then good quality welding electrodes and shielding gas to protect the weld metal on the outside. And then clean, pickle, and passivate afterwards. In other words, get rid of that oxide, expose a fresh surface, fresh chromium to the atmosphere, and you will prevent corrosion forming there. If you look at this diagram that I have on here now, this is a diagram developed actually by Damian Kuteki and others. It's called the WRC 1992 diagram. And you can plot your nickel equivalent and carbon equivalent onto this diagram. And where you basically should be is in the FA region of this diagram. That means that a little bit of ferrite will form first, and that will protect your grain boundaries against the hot cracking. If you look at where the 304L is, it is very close to the lower boundary, and that's not where you want to be. If you weld the 308L, you can see that with dilution, it will move it a little bit closer to the 308L dot. And if you have multi-layer welds and you keep on welding with 308L, you will be safely inside that region. We will look at the same diagram for 316L as well. If we look at the 304L processes, consumables, and shielding gas, first of all the arc welding processes can be used, TIG, stick, MIG, flux cord, metal cord, sub-arc, all of them. I only look at the AWS classifications, but of course there are EN and ISO ones as well. The AWS ones are probably the best known in South Africa at this stage. You must avoid sensitization problems by using the L types. In other words, in the welding rod, it will be less than 0.03% carbon. You also get titanium stabilized grades, then the carbon will rather react with the titanium than with the chromium. If you have flow problems, a little bit of silicon will solve that problem, especially when you do MIG welding. It's useful to go to a 308 LSI. Then in terms of shielding gas, Afrox got Stain Shield Plus, and Stain Shield Heavy. And that it depends on the thickness of the material. The plus gives a little bit of a warmer arc than the Stain Shield, and the Stain Shield Heavy give the warmest arc. HP argon or Stain Shield TIG for TIG welding, always purge with HP argon. That's the best purging gas that you can get. And then our manufacturing industries team, this is the team that I am in Afrox. We are available to help large welding customers with the correct choices and procedures. Then if we move on to the 316L, the three key issues are exactly the same. You weld 316L always with 316L. You don't go to another type of stainless steel. But a very, very important thing here is if you look at the 1992 diagram for 316, you must make sure that the electrode or the welding consumable that you buy has a composition that is very close to the middle of the FA region of that diagram. And the typical Afrox one is there. And any other reputable manufacturer of electrodes or consumables will know this and will also give this like this. You get people that will not give it to you like this. Don't buy those electrodes. You will have hot cracking problems with your 316. If we look at the consumables, the same AWS codes are used, except this time you use the 316L type, and the gases are the same, and of course the manufacturing team is available to assist. Let's look at a typical hot crack. Now, hot cracking takes place on the dendrite or the grain boundaries, and right in the middle of your weld, on the center line. That is where all the dendrites get together. Remember that solidification takes place from the size of the weld, from the cold base metal towards the middle. So right in the middle is actually where those dendrites meet, and that is your most susceptible zone. So usually, not always, but usually, excuse me, you will see your hot crack appearing in the middle of the weld. Usually the welder can see it appear. There's no delay. It appears on solidification. Once it's solidified, there's no hot crack. A hot crack will not appear after solidification. Sometimes you can't see them on the surface. Then you need to do radiographic testing. Most of the time they're open to the surface though. It's better and cheaper to have the right solidification path. In other words, make sure that your consumable is in the FA region of the 1992 diagram than to repair afterwards. Welding repairs are very expensive. Then if we look at the 2205, the key issues there, it's a little bit more complicated. The first key issue is getting the phase balance right in the weld metal. You need 40 to 60% ferrite. The balance austenite, of course, because there are only two major phases, 40 to 60% austenite balance ferrite will also be right. Then your solution here is to weld with 2209 type electrodes. The 2209 actually is enriched in nickel to stabilize the austenite and make sure that you form enough austenite on cooling. The next slide will explain what I said now. You also need to control the heat input. The higher heat input, the more austenite you will form. The lower the heat input, the more ferrite you will form in the weld metal. I'm talking about the weld metal specifically now. And then you need to avoid long arcs or long contact up to work distances, because if you get any nitrogen contamination from the surrounding atmosphere, which usually is air, then you will strongly stabilize your austenite and your phase balance will not be right. To explain this, let's go back to the diagram, and you look at the nickel equivalent there. And your nickel equivalent are the elements that will stabilize austenite. You can see that nitrogen is 20 times as effective as an austenite stabilizer than nickel. So nitrogen, you don't want your duplex stainless steel weld metal to be contaminated by any nickel. Then, if we quickly look at this phase diagram, you will see there, if I move my cursor, where your high nitrogen 2205 and your low nitrogen 2205 are, and that is what we're looking at. This weld metal, if it solidifies first of all as ferrite. In other words, you have solid here that is 100% ferrite. On this line, the ferrite solvus line, upon further cooling, you start forming your austenite, your gamma. Now, because welding is not equilibrium conditions, you actually have very fast cooling. If you go too fast through this region, you will not form enough austenite. In other words, that explains what I said before, that if you weld warmer, and you will have slower cooling, more time to form austenite. And if you weld with a higher nickel content electrode like 2209, you will move towards the left-hand side here and have a larger austenite plus ferrite regions and that will give you more time to form austenite. The other key issues are exactly the same as for austenitic stainless steels. I'm not going to repeat it here. Then also for duplexes, you can use all the processes, classifications from 5.4, 5.9, and 5.22. For 2205, always use 2209. For these, you want to avoid shielding gases with nickel or CO2 in them, because carbon or nitrogen contamination will promote austenite formation. Here you want to look at normal Afrox stain shield TIG for all processes, or TIG plus also for all processes. Before the 2209 weld metal was developed, some shielding gases had 2 to 5% nitrogen in them to actually assist with the austenite stabilization. You must stay away from these shielding gases because nitrogen is very destabilizing to welding arcs. And if you use 2209 with a nitrogen containing shielding gas, you will form too much austenite, that's for sure. And then once again, our manufacturing industries team that consists of myself, which is an international welding engineer, and 3 international welding specialists, we are able to assist you. If you quickly look at the joint preparation, all common joint preparations are suitable. Machining or grinding, but don't use carbon-containing abrasives. Remember that stainless steels have high thermal expansion, so do not open. But if you weld materials with high thermal expansion, you want to limit the volume of the weld metal, and you also want to limit the amount of heat that you put in. So keep them as narrow as possible, but widen them up enough to get fusion. And then balance the welding sequences and the weld metal volume on both sides of a plate or on both sides of a pipe in order to balance the distortion. Thank you very much. That is my story. Thanks for the opportunity. I'm going to hand back over to Shannon.
Thank you very much, Arnold. It's so interesting to note that thanks to their reasonable levels of corrosion resistance, their good weldability and cost remain the most commonly used grades of stainless steel. I'm going to take a moment now to hear from our audience. I'm going to launch a poll here. I'll also allow the panelists to vote just for interest's sake. And this is about specifications, how often you specify stainless steel, what sort of problems you experience. So if you want to have a look at that, it's on your screen now. We'll just give you a few minutes to answer those questions. You'll see now how often people experience corrosion problems. It seems most people so far, of the few who have voted, do experience corrosion problems at their plants for stainless steel. Definitely we'll be in touch with Simon after this to maybe help you out with that. It also seems that the majority of people use austenitic 316 stainless steel for their plant or processes. I will share the full results with us as soon as we've answered. I'll just give you a few more seconds. Right, we've had about half of our attendees vote, so I'm going to end the poll now. And let's end that. Right, and it looks like we'll share those results. You can see that, unfortunately, most of you do tend to suffer from stainless steel corrosion, with more than half of the attendees stating that. And the type of stainless steel, majority of you use austenitic 316. And as Simon mentioned, that DUPLEX one might be the one that you might want to consider. And then we see here, it's exactly 50% of who has used DUPLEX and who has not. Right, thank you very much for voting. I'm going to stop sharing that now. Right. We're going to, I just wanted to remind you again that our Q&A function is enabled. So please do send us your questions. Some of them have already been answered by our panelists, but otherwise we will discuss it after the webinar. We move back now to Simon Norton of Chemical Investigation Services, who will delve a bit deeper into the world of stainless steel corrosion.
Thank you, Shannon. Thank you very much. Good afternoon, everybody, again. Allow me just to share my screen with you. Well, I'm going to tell you about some interesting stainless steel corrosion tales that relate to sausages and car parts. The first failure concerned a degreaser tube failure. This is a plant where there was fluid spraying all over the plant. This particular company had a new cooling system installed in a degreasing device which degreases automotive components. The automotive components are aluminium. They are coated with various tube forming lubricants and other lubricating materials used in their tube forming application. They then degrease it prior to some other part of their process. A new cooling system was put in for the degreasing fluid, and the cooling system was supposed to be 304 stainless steel. In fact, it's supposed to be 304L, but it was 304. However, let's see what happened. This is the German manufactured degreasing machine. Unfortunately, I didn't get a better photograph than that. However, it gives you an idea of what we're dealing with. And this is what the part of the cooling system looked like after the degreasing fluid had, for some reason, deteriorated and attacked the stainless steel. The fins are aluminium. The pipe is not. This is what the 304 piping from this degreaser looked like, and you could see that there's some form of degradation that's occurred to the degreasing fluid. Something very serious has happened here. And you can see in here that the degreasing fluid should have been a clear to slightly straw-colored fluid, and it would have taken all the oil off the aluminium components, and then the fluid, being hot, goes through the cooling unit to be recycled through this particular machine. But something terrible happened here, and within 3 days, and that's why I would like to emphasize to those engineers listening that these 304 stainless steel AISI 304 austenitic pipes were pitted within 3 days of installation. Within 3 days, these pipes pitted. And I'll show you shortly what actually happened.
Simon, just before you carry on, you're not sharing your screen, so we actually can't see those images. I'm not sure if you'd just like to share that.
You should have sent me that. Okay, sorry, my apologies. Can everybody see?
Yes, thank you.
Sorry, thank you, Sharon. Sorry, my apologies to you. This is the degreasing device. That's what the cooling tubes looked like after they had failed. This is what they looked like after we cut open the pipes. This is the degraded degreaser inside the pipes. This is what the pipes looked like when we cut them open. And after we cleaned out all the sludge and material to actually have a look and see what happened to the surface of the pipes, this is what they looked like. You can see here that the insides of the pipes are severely pitted, and in some places they had pitted right through and the pipe failed. You can see there's a particular pit from the photograph taken from the outside. So the moral of this story is an alternative material should have been chosen. The plant should have had better control over the degreasing fluid. They had actually bought a degreasing fluid from a European-based supplier that had given them very reliable service that had been inhibited against failure during operation. But for cost reasons, they had decided to remove that product and choose another product which they bought from the Far East. And that product had not been stabilized against failure. The product then turned acid, and it attacked the 304. What also happened was that because it wasn't stabilized and the product was tetrachloroethylene, it had chlorides in it, and it degraded and became hydrochloric acid. The chlorides then just attacked the stainless steel, and that was the end of the cooling system. So this illustrates the point that you need to look at the entire system and all the possibilities that could occur before choosing your stainless steel. And it also emphasizes the point that pitting corrosion can be very, very fast and very, very damaging. My second little case that I want to show you doesn't directly concern stainless steel, but stainless steel is implicated in this problem. An industrial laundry carries out frequent, huge loads of laundering of hotel and guest house sheets, pillow slips, and towels. And they usually use a detergent to do the process. And what has happened in South Africa, for those of you who are living here, you will know. For those who perhaps not been to South Africa, we have lots of sunshine here and lots of beaches and people love to come here. And when they go out to the beach, they like to put on tanning creams. And these creams give them a very healthy look. So when they go back to their winter climate, they can look very, very healthy and well. But the problem with this material is that it actually comes off on sheets, pillow slips, and towels. And this particular industrial laundry was set the problem by hotels to actually to get rid of this problem. They said the washing wasn't being done properly. So this is part of the industrial washing machine that failed. The interior consists of stainless steel. We didn't check that because that's not where the failure occurred. Just out of interest, this material here is pre-galv, what we call pre-galv or continuous galvanized sheet with a very thin zinc coating. This material here is probably a ferritic stainless steel in the center. This is the actual drum in which the washing took place, but that was not the issue. The drum, because it's loaded with so much water and washing, has to be very well balanced. And the drum had a balancing disc. Now, this was a design, definitely a design fault. If you look on the back here, this is a carbon steel balancing disc attached to a stainless steel drum. Now, when we first came to look at this problem, we thought that we might have a galvanic corrosion problem. And I think the reason I showed this, because although it's not a stainless steel failure, I wanted to introduce the concept of galvanic corrosion, because that can occur with stainless steel. And essentially it happens because two dissimilar metals are in an electrolyte and there's an electrical contact connection between them. And when those three conditions are met, electrolyte, two materials far apart on the galvanic series, and electrical contact, provided there is the right ratio of surface areas, you will get corrosion. So in your design, you have to be very, very careful. It is possible that in the case you see in front of you, the large stainless steel drum, which would have been passive and therefore noble, and the smaller mild steel disc, which would have been active and would be the anode, could have corroded because of a galvanic reaction. We don't think it did, but there is a possibility that it might have contributed to it. Just out of interest, there is the galvanic series. And if you look at the top here, you'll see that towards the noble end, stainless steel 316, stainless steel 430 sits over here. And right down the bottom here is low carbon steel. So if you go back to this photograph, you've got two materials far apart, immersed in an electrolyte and with a contact position. And then the ratio of areas, well, you've got a large stainless steel drum and a much smaller anode made up of the mild steel. However, we think this is not what actually happened. When they had to put in this material to get rid of the staining on the sheets, the pillow slips, and the towels, and use a special form of stain remover, they actually used a material that contained very, very corrosive halogenated material, fluorides, which are as problematic to stainless steel as chlorides. And what we did was, in the left-hand beaker, we put test plates in a solution made up with just the detergent. And on the right-hand one, we made a solution with the detergent plus this so-called rust remover or stain remover. We then put them on magnetic stirrers. We turned the temperature up as if it was in the washing machine, and then we left it running for the night. And you can see the effect. That's what they looked like when they went into solution, the steel plate from the back, mild steel, beautiful condition. This is what the ones look like with the stain remover. The solution shows clearly corrosion. That's what a plate looked like just with detergent. This is what a plate looked like when you use the stain remover. So you can see that this particular stain remover attacked the carbon steel. It attacked the drum that I showed you early on. Go back a photograph here. It attacked this material here. It attacked this over here. And the moral of the story is what we did was suggest to them that they use either 316 or better still put a DUPLEX 2205 disc on the back. They did that and they never looked back. Their washing machine continued to operate in an industrial action. My last case, before we go to questions, concerns sausages, and it concerns stress corrosion cracking. This particular company manufactures millions and millions of Vienna sausages here in South Africa, and they use a particular process. They take meat, they then put it into a machine where they make up the sausage with all the lovely spices and flavors and the meat. They shape it into a sausage, but instead of putting it into what we call a sausage skin, they actually form the skin by drenching it in a kind of a chemical, but a natural material. And after that, they need to dry it to form the sausage so they can send it off for packing. So here we go. There is the dryer that dries the sausages at 82 degrees centigrade and 35% relative humidity. There's the conveyor belt on which the sausages move. And all these wires started to break. Little pieces of wire were then found in the sausages, and there was a complaint from customers. This is what looked like when we magnified the sausage, magnified the wires. You could see the pits, and then we saw the stress corrosion cracking and the cracks all over the wires. And from there, it was quite relatively easy to get to the solution. This is what the belt looks like very close up. That's one of the stress corrosion cracks in the wires. And we realized then that what was happening was the wires obviously under tension from the formation of the wire, so there's residual stress. The temperature in the cooker, well, in the dryer, was 82 degrees centigrade, so there's a high temperature. There were chlorides used to drench the sausages, and you've got the combination sufficient for stress corrosion cracking of 304. This was 304 stainless steel, and the other side fittings that I showed you here, these fittings were 316. So what they needed to do was go to the supplier and say, look, we'd like a DUPLEX stainless steel belt so that we can actually resist stress corrosion cracking. This just gives you some idea of what happens there. The Vienna sausages, the arrow points to where the drenching fluid comes out. There's the sausages coming out from the drenching, and they then hit the belt, and they all hit on the outside here. And in the next image, it's a live one. I'm just going to, you won't need to worry about the sound, but you'll actually see this moving, and you'll see all the sausages falling out of the machine. So they've been drenched with a calcium chloride mixture. So there's high chlorides. They fall on the outside of the belt. That's where all the wires broke. But there's one last little catch to all of this, and that is that you get a biofilm formed on the wires because you've got so much food and material there. And that biofilm can actually impact the resistance to corrosion of the 304. So this was another example of how careful choice of materials can make a huge difference to your operations in using stainless steel. So when you select stainless steel, first ask, what is your environment? How much chloride? Is it acid? What type of acid is it? What's the temperature? Will it be exposed to stagnant water? Are you going to weld it? And how much are you prepared to pay? I would like to thank you for participating in this afternoon. Because of our time limits, we're probably going to have to go straight to questions and answers. Thank you very much, and over to you, Shannon.
Thanks very much, Simon. As you said, we'll move now to the Q&A. The first question I'd like to ask is one we received from a registrant before the webinar even began. And he asked, what happens when stainless steel is subjected to diluted acids, as he's currently experiencing failures on stainless steel 316L piping that is carrying 98% sulfuric acid? I think, Simon, you can address this question.
Yes, Shannon, I'll address the question. The question, the company concerned was pumping 98% sulfuric acid, I believe, through 316L piping. And I'm not sure what sort of failures they were experiencing. But what I'm going to try and do now is just show them a diagram, and based on, I'm assuming that they're getting water in their sulfuric acid. They mentioned processed fluids. I'm not sure what those processed fluids would be. Let's just see if we can get this up here. I must just share my screen here, so apologies while I get that organized. Right, to the gentleman who asked about the sulfuric acid, these are known as isocorrosion diagrams, and they show the rate at which austenitic stainless steels would, in naturally aerated sulfuric acid of chemical purity, show uniform corrosion. Now, the gentleman concerned mentioned that he had a 98% solution. So if you look along the bottom x-axis, you'll get 80, 90, 98%. If you look at those two diagonal lines, the top line is 316, 70% chromium, 12% nickel, 2.5% molybdenum. The 316 line, and the bottom line here, 1810, will be the 304 stainless steel. So if this sulfuric acid remained pure and he was at 98%, then he would have found that he could actually operate up to about 40 degrees centigrade with his 98% sulfuric acid and only show 0.1 millimeter per year uniform corrosion in his piping. However, he had some sort of failure, and he mentioned that processed fluids got in. So if he diluted himself, if he was diluted, and let's say that he diluted back to 80%, well, then he's going to suffer very, very high rates of corrosion of his 316 piping. Now, what he needs then to do is to make a decision which is going to be technical and it's going to also be financial. The next visual will show you where he'd be looking. If he decided that he's going to use either DUPLEX stainless steel or another super austenitic called 904, then he could have his hydrochloric acid, his sulfuric acid could be diluted back at any value, and he would be inside the 904 uniform corrosion level, and he would be safe and sound. But he has to remember that 904L, which was designed to work with sulfuric acid, is about 2.5 to 2.8 times more expensive than austenitic 316. So his next option is to actually try to use either DUPLEX. He could use DUPLEX stainless steels, but he needs to find out to what extent is the dilution taking place. And the second question I've got to ask him is, if he's got chlorides in his process fluid, then he's going to be in big trouble. If he's allowing leaks with chlorides, he's going to be in big trouble with pitting and crevice corrosion in his pipe. So he's going to need to do an exploration of what happens with his process fluid, and he's going to have to make a decision as to what sort of material to use. If he wants to, you'd have to send us all the full details before we could come up with a solution. I hope it answers the question.
Thanks very much, Simon. I'm sure that gave him some information that he did need. I have a question here from Johan, and he asks, can a stainless steel nozzle be welded on a carbon steel pipe when using domestic water? I'm not sure if maybe Arnold would like to address that one.
Arnold, you want to pick that up?
Yes, there's no problem with that. Just 2 points there. The first one is I would use as filler metal, not another austenitic, because of the cracking problem. I would use a simple carbon filler, something like 7018 or 70S6. And then this is actually the situation that Simon described with the washing machine, just in reverse. It's a small stainless steel nozzle that you weld onto a large carbon steel pipe. So a very small cathode, very large anode situation is good. If it was the other way around, would have been bad. So yes, you can do it, no problem.
Thanks very much, Arnold. Another question we have is from Mario, and he says, when inspecting DUPLEX stainless steel for iron contamination, what will be the best test to perform?
I'll start to deal with that. I don't know what he means by iron contamination, but if you've got stainless steel piping and you've got iron contamination, the first thing you need to do is get rid of it, because you shouldn't have it, because it can set, if it adheres to the surface, you're going to get crevices under that iron, and you're going to get pitting, or you're going to get crevice corrosion. What he probably needs to do is passivate it and clean the surface. If it's severe, then he needs to pickle it. Once he's pickled the surface, it'll remove a nanometer layer of the material. The chrome oxide layer will completely reform, and he'll have a pipe that's in pristine condition. If it's just, I don't know, iron filings, or I don't know, incidental iron degradation that's fallen on the surface, then he needs to just rinse the surface, passivate the surface, and he should be all right. Arnold, I don't know if you want to comment on that.
Yes, I agree with that. I think what may be meant by iron contamination is actually contamination by the carbon that is in steel. That might be what is referred to. And then you will see pitting all over the place, and you'll see wherever there is contact between your carbon steel and your stainless steel, there will be corrosion on the stainless steel.
Thanks very much for that. Another question we've got is, this person is currently having issues with stainless steel 316L piping, which keeps failing on the welds of the flanges or anywhere where it's welded. The welds would fail within a week after the pipe has been installed. The piping is used for transporting 98% sulfuric acid from a 600L batch tank. There is currently no surface finish being done on any of the welds. Could this be the main issue?
Yes, Shannon, that could exactly be the issue that he has at the moment. We've spoken about it. When there is oxidation on the surface, then that surface is depleted of chromium, and your corrosion resistance will go down. So pickle and passivate on the outside. On the inside of the pipe, you have to put a shielding gas on the inside, in other words, purge, so that there is no oxygen available on the inside of that pipe for the chromium to oxidize. So the pipe must be purged totally with high purity argon before you weld. Usually with pipes, you cannot back grind the root of the weld. In other words, it's an open root. You cannot clean up afterwards because the pipe is welded shut, so please purge. Another problem that can also cause those quick failures are actually a lack of sidewall fusion also in the root. And then if he is doing a MIG welding, it might be useful to go through to the grades that contain silicon, just to make it easier to fuse and to flow. So yes, that's my answer for that.
It
Shannon,
does seem that the same person is using argon gas, so not sure if that has any implications.
I just wanted to show a photograph here, if I might, that will just illustrate for this fellow what's actually happening. If you could just give me a moment. This particular piece of piping, it's quite clear that whoever welded this pipe, and I think Arnold will agree on this. Can you hear me, Shannon? Can you see the picture?
Yes, we can.
Can you hear as well?
Yeah.
This particular photograph shows what happens when they did not shield the welding correctly. And you can see the heat tint at the arrows. Where that heat tint occurs, it will extract the chromium from into the oxide layer, weaken the stainless steel. It loses its ability to be stainless steel, essentially. So the critical, ignore the cracks at the bottom. That's not relevant to this particular person's problem. But if they shield this correctly, there'll be no heat tint there, and then they will have a proper weld. If they get it, if it's looking like this, if they now go to their failed pipes, cut out the samples that have failed, slice them open, and if they look like this, then they've got problems, and then they need to consult. They must start purging. They must start shielding their system and purging the system. There are actually photographs that can tell you the level of oxygen. I think in this particular case, this particular, I could almost tell that there was something like 500 ppm oxygen in the pipe just by the color of the weld and just by the color of this heat tint. Okay.
Thanks very much, Simon. I think we'll just take one more question, and that is Mario again asks, in the food industry, when requested to use 304L stainless steel, what will be the best prep for this material? You have mentioned, this is very technical, perhaps Simon, you can just look at your Q&A panel, and then if you can elaborate on that.
Apologies. Mario, what we're referring to there is if you can and you can electro finish your stainless steel, by RA we're referring to the surface roughness. So for instance, if you passivate a surface, all you're really doing is just taking off tramp iron and small bits and pieces. If you pickle the surface, then you are actually taking a nanometer layer of material away, and a completely fresh chrome oxide, iron oxide layer forms, and you completely restore your pipe. So if you pickle your pipes before you use them and install them, that could be one way. The other way is to actually electro-finish your piping by sending it to an electro-finisher, where you get a beautiful, beautiful surface, and it increases the critical pitting temperature and your critical crevice temperature as well. And you don't, if it also makes sure that you don't get microbiological or food sticking to the surface, so that you get contamination of your piping. I hope that answers the question.
Thanks, Simon. And he says, awesome, thank you. So I think it did answer his question. And then the final question we've got is from Yandre, and he says they've been using 98% sulfuric acid on their plant. Previously, they used carbon steel piping, stainless steel piping, 304, 316, 904L, and DUPLEX, but it all failed. We are now considering alloy 20. What is your opinion on its use?
I don't know what alloy 20 is. I'd have to look it up, but I'm very concerned that they have used 904 and 904L, which was designed to be used with sulfuric acid, and they've used DUPLEX. I don't know which DUPLEX they've used. If they've used DUPLEX 2205, maybe they had a problem, but if they'd used super DUPLEX like 2507, then they shouldn't have had a problem. It looks to me like there might be, and they don't say what problems they've had, they say failures. Does it mean they've had pitting corrosion, crevice corrosion, stress corrosion, cracking? I don't know. But if they've had failures, I'd like to know what those failures are. If they're getting chloride contamination or fluoride contamination, then that will cause them big problems. I somehow think they don't need to go to highly expensive alloys, as I presume alloy 20 is that. But I think there's something deeper there that has to be examined before they actually make a further decision. It sounds very unusual. Arnold, I don't know if you want to comment on that.
Simon, I agree with what you say. If I remember correctly, alloy 20 is one of the very high nickel alloys. And it will be very, very, very expensive. I agree with you. I think it's some sort of contamination, or maybe the temperature is too high. But yes, I agree with what you say.
Well, thank you very much. No problem. I think that's all the questions we've got for now. It's all the time we have as well. We will pass on any contact details should anybody need to be in touch with any of our panelists. I thank you very much for participating in our live Q&A. If you didn't get a chance to ask your questions, or we didn't get a chance to answer you, we will connect with you after the webinar. I'm just going to share a screen here with you. And Chemical Investigation Services can offer you expert support when it comes to selecting or troubleshooting stainless steels across industry. And you can reach them on 082-831-2924 or email chemdetect@iafrica.com if you have further questions on this. I would just like to say thank you so much to our panelists, Simon Norton from Chemical Investigation Services and Arnold Meyer from AFROC South Africa for joining us today. And of course, thank you to our attendees for taking the time to log in and hear about the essentials of stainless steel with case studies in corrosion. I'm going to quickly move across to Simon now. I think he's got a few words he'd like to say.
Firstly, I'd just like I must unmute. Right. I first want to thank Arnold Meyer from AFROX for being a guest on our program. Arnold, thank you very much. I'm sure that when people contact me, and we're going to be talking to you soon about welding issues, that's for sure. I want to thank Engineering News and Creamer Media for facilitating this webinar. And finally, I want to thank everybody who attended. Thank you very much. I'm sorry we can only squeeze in the very essentials in this short period, but we want to let you know that we're actually probably planning an advanced stainless steel corrosion seminar or webinar where we'll be talking in greater detail, because we've got plenty more material to tell you about, and probably I will be on this again, and we'll be able to give you some more information. If you need to talk to us, please contact us. You've got our contact details and we'll come out and sort you out. Thank you very much. And thank you to Shannon for being a wonderful host.
Thank you very much, Simon. I'd just like to let everybody know that the recording of today's webinar will be sent to you in due course. We will also streaming live to YouTube, so of course you can get that link from our YouTube. That's the Creamer Media YouTube channel. And if you have any additional questions, please do be in touch. You can reach me at shannon@creamermedia.co.za. Thank you so much for joining us. Thank you to our panelists. Stay safe, stay well, and goodbye.